Welcome, everyone. It's a pleasure having you here, and greetings and Happy New Year to everyone. And we are delighted to have you joining us today to our what marks the first webinar in our 2025 series. So it's an organized webinar by the Spatial Analysis and Simulation Lab community as part of our ongoing commitment to fostering academic dialogue and research collaboration. We aim to host and engage discussions on cutting-edge topics related to spatial analysis, urban simulation, and environmental challenges. We encourage you to visit our website, and actually I'm sharing the screen right now. This is our website, and these are our research interest points. In addition, we have a series of webinars. These are the previous webinars that we have conducted in the last year. And actually, we have established in August 2024, so we're just a young community and lab. And we are doing also as well workshops and dealing with some tools that we are conducting by ourselves or by our team. And they're all open source if you would like to take. And these are the coming announcements, which one of them is today's webinar. And this is our yearly report, which is just our first year report, what we have done. And if you'd like to listen and see our webinars, this is our YouTube channel containing all the webinars, and some of them are audio only if you'd like to listen to them, and some of them are audio and video as well. Now, moving on to today's event, we are honored to welcome our distinguished speaker, Noel Cressie, if I'm pronouncing your name correctly.
Yes. Thank you.
Thank you very much. And who will speak on the important and highly relevant topic, which is mapping and monitoring carbon dioxide from space. Professor Cressie will share insights on how satellite-based technologies are being used to monitor CO2 emissions globally and regionally, a critical area of study given the ongoing climate crisis. Before we begin, let me briefly introduce our distinguished speaker. Professor Noel Cressie is Distinguished Professor at the University of Wollongong, Australia, and Director of its Center for Environmental Informatics, which is an interdisciplinary group conducting research in spatio-temporal statistics, satellite remote sensing, and broader fields of environmental science. He is author and co-author of 4 books, 3 of them on spatial and spatio-temporal statistics, and of more than 300 peer-reviewed publications. His recent research involves hunting for atmospheric carbon dioxide sources around the world and focusing on Antarctica environmental future. Noel is a fellow of the Australian Academy of Science, of the Royal Society of New South Wales, and of a number of other learned societies. We sincerely thank Professor Cressie for joining us and sharing his expertise with our community today. We look forward to an engagement presentation and a lively discussion afterward. Please feel free to ask questions and leave them within the chat box, and if you would like to discuss them after the presentation. And please free to participate actively throughout the session. Thank you once again for being here, and without further delay, let's begin. Professor Noel, the floor is yours.
Thank you very much, Nabil, and it's a great pleasure to be here, if virtually. I understand it's 10 p.m. in Cairo, and I congratulate you all for staying up for this particular presentation. I'm going to talk about something global, and I realize that your group tends to be looking at quite local things, local environments, and I'm quite aware that we all live in a local community, and this sort of thing is, where we live and how we live in a future climate is very relevant. But on the back of this are long-term global trends that we need to understand. So first of all, carbon dioxide is a leading greenhouse gas, probably all aware of that. The data that come from satellites are spatio-temporal, and this talk is about exploring those data. We're going to use some new filters to do some spatio-temporal modeling. And the data that we're using is from a satellite. This is an artist's view. This is a satellite called the Orbiting Carbon Observatory 2, flying at about 700 kilometers above Earth's surface. Okay, so carbon cycles in the Earth system, and in the terrestrial pool, carbon is a very important component. It stays there. It forms things like oil and gas and coal. The problem with carbon is that when it comes into the atmospheric pool, it causes a great deal of trouble. And as a consequence, we end up with carbon dioxide, a leading greenhouse gas. This is sometimes called the Keeling curve. It's a famous curve which shows you what carbon dioxide has been doing since 1960. And that curve is showing in the northern hemisphere in green and in the southern hemisphere in blue. And the two particular sites that are being used to monitor the carbon dioxide, one, the green one is on top of Mauna Loa, which is in Hawaii, and the blue one is in Tasmania, which is the state of Australia. And it's on the west coast, so it gets very pure air coming across in the Southern Ocean from South Africa, basically. So there's no contamination with nearby fossil fuel sources. This is what carbon dioxide looks like in nature. So let's talk a little bit about the satellite. The first version launched in 2009, but it failed to reach orbit. OCO2 launched on 2nd of July 2014, and I was at both of the launches, and very, very, very sad about the 2009 failure, but very, very happy about the 2014 success. Took 5 years to put together another satellite and launch it, and that particular satellite is still measuring carbon dioxide 10 years later. In fact, I was in California at the 10-year anniversary of the launch of the satellite, and we ate some very nice cake, the 10-year anniversary cake to celebrate that. So it has certain properties. It gets around the globe 14 times a day, but it doesn't get back to where it started from for about 16 days. And it tends to trace out a ribbon, and that's the sort of ribbon that we see when we do this. There's something called the Basic Aerial Temporal Unit, which I'm going to use in this talk, and that is a 1 degree by 1 degree by 1 month resolution. Now, of course, the satellite is taking many, many observations every minute, and so a certain amount of aggregation is needed. I've worked a lot on the error structure of the satellite, which I won't go into. What I want to do is come up with some summaries of what we see in the satellite. So we're using something called version 10R. There are lots of different versions, and every version is better than the last one. This particular version is 90 months of data, which is pretty good. As I mentioned, it's sort of about 8 years worth. And I'm going to aggregate the daily data to monthly data, and I'm going to take Earth's surface and split it up to 1 degree by 1 degree basic aerial units. That's important to know how we're going to split up Earth's surface. Many of these BATUs, or basic aerial temporal units, are actually empty because they don't have any observations in them, or at least there are too few. So there's a bit of post-processing going on after the satellite data is retrieved that I do, which involves looking at a particular 1 degree by 1 degree cell, and then looking at the time series of that 1 degree by 1 degree cell over the period of 90 months. And sometimes there is no data for 1 month, and then there is data the next month. It just depends on the level of, it's actually seasonal. It depends also on the solar zenith angle, which is the amount of sunlight that allows the satellite to see a reflection from Earth's surface. That's one thing I forgot to mention. The satellite actually is a daylight-only satellite. it relies on reflection of energy from Earth's surface. In the post-processing stage, what we did is define a window, a 4-degree by 5-degree window around these 1-degree by 1-degree BAUs. Nabil, I just want to make sure that you can see that slide. So this bottom formula is really, really important, because what we're going to do is take the average of the carbon dioxide in that 1-degree by 1-degree cell at that particular month, and we're going to come up with a number, and that would be the average carbon dioxide. And that particular quantity is what is really, really important for us, because I'm going to work with that in both a spatial and temporal context. So here we are, we have Earth's surface. I want you to imagine the globe. And as we know, we can split up Earth's surface into northern hemisphere and southern hemisphere, and into tropics. So we can have the southern tropics and the northern tropics. We have the extratropics, which is beyond 23 degrees north and further south than 23 degrees south. And the tropics is everything between 23 degrees north and 23 degrees south. And I'm very interested in what's happening in those particular regions, because we know very well that the effect of carbon dioxide is very what we call zonal. It means it depends on what latitude you're at. And pretty much everything at the same latitude has the same carbon dioxide. So there's a strong gradient in carbon dioxide that is latitudinal. So for that reason, it's important to make these regions stick with the idea of latitudes. So most of the carbon dioxide variability is in the northern hemisphere, and we have in the northern hemisphere lots of things going on. We have a lot of photosynthesis from the forests, because there's a lot of land mass in the northern hemisphere. And then we have anthropogenic activity, of course, and that's commercial and industrial. And that's part of the problem with our changing climate, our warming climate, is that a lot of the industrial activity is the emission of fossil fuels. And the fossil fuel part, is because it used to be in Earth's under the ground. And so in the terrestrial pool, it's harmless. We pull it out of the terrestrial pool, we burn it, and then carbon comes back. It gets into the atmosphere, becomes carbon dioxide, and is a greenhouse gas. Now, ideally, what we'd like to do is take that carbon and move it back into the terrestrial pool. And sometimes people try to do that, and it's called carbon capture and storage. Probably the most effective way is for a tree to absorb carbon from the atmosphere, form its wood product and its leaf product, and into the roots. And then there's microbial activity of carbon in the roots. But that's a very slow process. What we're doing is pulling coal and oil and gas out of the ground very fast, and we're burning it very fast. And so we're emitting into the atmosphere really fast, and we can't handle it. We're just getting too much all the time, and I'll show you how that works. So this is another view of that Keeling curve. And I want to note that it starts here at 395. It doesn't start at 0. And way back in 1960, that was at about 340. And now it's worked its way up into the 400s. So what we have is this global carbon dioxide. And you can see the, excuse me. You can see the periodicity, the way that trees absorb carbon dioxide when they have photosynthesis, and then they emit carbon dioxide when the leaves decay. So here is a way to deal with filtering of that particular graph. And I've computed something called the anomaly, which gets rid of a moving mean. It essentially gets rid of the trend term, and it leaves behind what we know happens, which is a very strong periodicity of natural fluxes, where leaves are absorbing carbon dioxide through photosynthesis, they're falling off the trees, and then they're emitting carbon dioxide when they decay. So we can see that, and it's a very nice, very simple graph. So this one is the picture of the difference. And you can see here what I've done is I've annotated the particular month with when the COPs were held. There was a COP in Egypt, I think, at Sharm el-Sheikh in probably 25, but these COPs.
It was like a few months ago. In 24, it was a few months ago.
Yes, it was COP27.
Okay, all right. So it's not on my graph because I didn't have the data for version 10R for that particular one. So thank you. So I'm pretty sure that COP27 didn't make any difference to this increasing graph. So we're looking at the effect of the COPs, and it doesn't seem to have made a lot of difference. Carbon dioxide is simply increasing without bound. But it's important to get rid of the natural cycle in order to see that. All right, so what we can do now is start working with that trend term, because that trend term is a yearly trend. We wanted to see what happens each month. And so in order to see what happens in, I don't know, the month of May 2018, we would look at the trend in 2018, May, and we would subtract the trend in April 2017. So we just make sure that we were looking at these increments and seeing how quickly carbon dioxide's increasing in this from month to month. And this is the trend term. And so when you do that, you end up with a curve which never, ever goes below zero. And I want to remind you that if we're going to do something about carbon dioxide, we have to make that trend term, this one, we have to make it negative. We have to make it flatten so that there's no trend at all, and then we have to turn it into being negative. And that is not happening. It consistently is staying above a value of about 0.14. And when I go to the next slide, this is a yearly trend. This says I'm going to compare May 2017 with May 2016. And I've drawn a dotted line there at 2 and 2 parts per million. That is now the yearly trend that's happening and has happened for many, many years back to 1960. The satellite has recorded it and come up with this yearly trend, which is obviously a smoother version of the monthly trend, but it never gets below 2 parts per million. What that means is, if this continues on, in the next 10 years, we'll add another 20 parts per million. And in the 10 years after that, we'll add another 20 parts per million. And in order to go to net zero by 2050, we're going to need to take that 2 parts per million and turn it into 1 part per million, and then turn it negative. So that curve that you're looking at does need to go negative. So it helps actually to see where all the action is. And it turns out that the action is in the northern hemisphere, not in the southern hemisphere. Now, I'm in the southern hemisphere, and we're all very concerned in Australia about carbon dioxide and our fossil fuel emissions. But compared to the activity in the northern hemisphere, it really is quite small. I've colored the northern hemisphere red and the southern hemisphere blue. I did that because there's a lot of ocean in the southern hemisphere, not so much land, and that does account for the fact that all of this cycling that you see in the northern hemisphere isn't actually occurring to any extent. So this represents what happens in the tropics, all right? The previous one was for the extratropics. By the extratropics, it's 23 north, further north, or 23 south, further south. This represents the tropics. And you can see that in the tropics, not much is happening. A lot, the periodicity is all in the northern part of the tropics and not so much in the southern part of the tropics. So what I did is I combined the tropics and then concentrated on the three regions, the northern extratropics, the tropics, and which is 23 north to 23 south, and then everything south of 23 south. And I colored that yellow. And I put them all on the same graph. And so I could show you what the natural cycle looks like and then what the trend looks like. And you can see actually the trend, whether it's in the northern tropics, or sorry, in the northern extratropics, the tropics, or the southern extratropics, it doesn't make a whole lot of difference. The trend, the slope of the trend is pretty much the same. It just takes a bit longer in the southern hemisphere to catch up to the parts per million quantity in the northern hemisphere. Okay, so I'm going to concentrate now on these quantities, these three quantities, and eventually I'm going to just really concentrate on the northern extratropics. So this shows you what things look like when it comes to those three different regions. Here's something important. There's a lot of seasonal structure. So what I'm going to do is concentrate on a particular month of the year. And I'm going to choose December, for example. There are a number of Decembers in the 90 months that I have available to me, and I've numbered them 4 through 88. There are 8 of them. And so what I'm going to do is look at what happens to the difference between the Decembers, all of the Decembers, and then take a look at that. So what I'm trying to do is get rid of the seasonal effect in a very simple way. I'm not fitting a time series to it. I'm not fitting any cosine, sine terms to it. I'm going to look at something I call A tilde and M tilde. And A tilde is what happens when we get rid of the monthly effects, and M tilde is when we get rid of the month of the year effects. So let's just take a look at what these particular December, January, February look like in terms of the carbon dioxide. The difference is actually the interannual variability of these anomalies. And you can see here, this very large lump here. And that's an El Nino. There are physical reasons for this, by the way. That's an El Nino phenomenon. This turns out to be a La Nina phenomenon. And this turns out to be a shorter El Nino phenomenon. These are well known from a geophysical point of view. But the cool thing is that carbon dioxide is able to pick this up. And those of you who have sort of, maintained an interest on climate and weather know that a lot of the world's climate and weather is determined by El Nino and La Nina. And El Nino is a warming of the tropical Pacific off the coast of Chile. And that warming is an El Nino, and the La Nina is a cooling. And that has a huge effect on rainfall and droughts in Australia, Indonesia, Asia, the United States, huge effect. And because everything's connected through teleconnection, has a big effect on everywhere else in the world as well. We could do the same actually with, let me just move that up. We can do the same with the trends. Notice I've split up things into the natural and then the more anthropogenic. The A is the natural and the M is the more anthropogenic. And so you can see similar phenomena. There is something interesting here, and I'll point it out a little bit later, but this is the COVID effect. This is what happens when you turn off all the industry and people have to go into lockdown. So sometime between around April, May, through to really November, or October, November, there's a very strong COVID effect, COVID-19, when the pandemic hit the world. But there was a snapback very quickly once all the industry came back on board. So what we've done is look at large regions, and what I'd like to do is to remove some of these effects and come up with these spatial anomalies, right? So we did temporal anomalies, and we have a nice graph time series. So what I'm doing now is I'm concentrating again on December, but I'm taking this moving window at 1 degree by 1 degree with a 4 by 5 around it, and I'm going to move it around the globe, and I'm going to capture the averages of the carbon dioxide. And that's something which I'll show you a picture of now. So this represents what happens in the Northern Hemisphere in the month of April. And there's a reason why it's red, is because there's a huge amount of outgassing of carbon dioxide in April. Now, that's something that we do know about. Perhaps we don't know that it's as strong as this and it's as regional as this, but this particular graph, which I came up with, I think is new. I've never seen it before, and it does come across very strongly for what the effect of carbon dioxide is in different months of the year. So this was what happens in August. What's happening is it's starting to take carbon dioxide in. It's breathing in. What we just saw in April was it was breathing carbon dioxide out. Now it's breathing it in. You can see it's going from yellow to green, and now it's going to go back to yellow in November. It's working its way back up again. So if we go back, you can see these. You can see the progression to a point in November where it's now at about 0, and it's going to go back up again. So this, I would like to show you, that's the Northern Hemisphere. It's highly active, but this is what Australia, this is what Australia looks like. And that's in March, that's as yellow as it can get. And in July, that's as strong as it gets, more like 3 or 2.5 on average for emission of carbon dioxide. The general feeling is that carbon dioxide is always being emitted. We never really get into a point in the Southern Hemisphere where there's a lot of absorption of carbon dioxide. So I'm going to now build something called the spatial contrast filter. And that will involve sort of getting things to a point where I get this moving window of 4 degrees by 5 degrees. I fix the time, and then I look at what month I'm in, and I subtract the spatial median of that particular month. So what you can see I'm doing is I'm getting into residuals. I'm trying to see, getting out of what we know and trying to work out what we don't know, and trying to look at what's sometimes called the interannual variation. And I can do the same for the A. Remember, A was the natural, and M, which is a more anthropogenic part of the natural variability. So let me move on. When I do that, I end up getting, and I've purposely chosen 2020 July, because that is the peak of COVID-19. That was when most of the economies were shut down. And you can see that in July, once I get rid of all the July effect and I get everything kind of even, so I can compare July to August to September. They're all comparable now. I've got rid of the seasonal effect. You can see that there's a lot of green. And when you're looking at green, you're looking at absorption of carbon dioxide, or at least you're looking at a very low impact of carbon dioxide. There's no acceleration of carbon dioxide at those locations. And what I've done then is also looked at July 2021, and I want you to compare them visually. And you can see here in Northeast Asia, China, Japan, Korea, there's so much more activity. We're now into the reds. We're into 0.6. Up here, we're into green, which is negative 0.3. You can see that what's happened is that all that industrial activity has come back again. And that is a cause for concern. So, why would we concentrate on the monthly series? Well, we can see things like COVID-19. We can see the depths of the pandemic. And we have a spatial contrast filter that shows a resurgent carbon dioxide compared to July 2020. And what I'd like to do now is plot the following summaries from January. So what you're seeing here is the COVID effect. And it's very deep. There's a sort of a spring out of COVID. Then, you know, there is some absorption of carbon dioxide here, but nothing like the effect that we had from COVID. So I could say that when we turned off all the industrial activity, the COVID-19 really only decreased carbon dioxide by a few percent, 5%, you know, globally, say. And then basically once industry got going again and people came out of lockdown, nothing changed. And in fact, that particular graph that we saw just kept going up and up. So the trend was barely affected by COVID-19. You might call that a natural experiment where, you know, we said, well, what would happen if we stopped all our industrial activity? And the answer is not much. And what we really need to do, of course, is to sort of get renewables going so that the industrial activity which remains is replaced by, not by fossil, the fossil fuel is replaced by things like wind and solar. And we do need to come up with ways to absorb more carbon dioxide to enhance the sinks and not wait for another COVID, which obviously we don't want to do. So where were the big increases? And this will show you where. What I did is I took December 2020 and subtracted the July 2020 just to see where the activity was, where the differences were. Remember, July is the depths of COVID. December 2020 is coming out of COVID. And those differences clearly occur, in particular, in July 2021, as we come out, they occur, we're not surprised, but they occur in Northeast Asia. Very, very strong return to industrial activity there. So coming towards the end of this talk, I'd just like to close off a bit. And, you know, this is more about what our planet is doing. There are people who look at what happens in different cities and how much carbon dioxide a city will produce. There are instruments now on the space station that is able to concentrate on a city and how much it's producing carbon dioxide. But generally speaking, globally, we have 1 petagram of carbon a year contributes to about 0.5 parts per million. So that means that our yearly increases of 2 parts per million results in the 4 petagram carbon increase in the atmosphere. And that's not going away. That is the net increase. We're actually putting out about 8 petagrams, but 4 petagrams gets absorbed by Earth in oceans mainly, I think, and some terrestrial, but we're not absorbing enough. So we only end up absorbing about half of the 8 petagrams that come from anthropogenic activity, from human activity. We only end up absorbing about half of those. And so we're sort of, we're not catching up. In fact, the Earth and its carbon dioxide is running away from us. The Earth is doing the best it can. What worries a lot of carbon cycle scientists is a tipping point where the oceans sort of get too warm, they get too acidic, and all that chemical activity which absorbs carbon dioxide might not happen anymore. And if that happens, what we saw as 4 petagrams a year will be 8 petagrams, and there will be a doubling. And so we will go up, instead of 2 parts per million a year, 4 parts per million a year. And then our climate will increase, well, exponentially at that point. And we can talk a little bit during questions, if you like, about what the effect is of this carbon dioxide on Earth's climate now, and what its effect will be, you know, in a year or 2 years or 10 years. We can talk a little bit about that later. So I do want to make a point that at the University of Wollongong, we're really interested in these problems. And what we need to do is get a hold of not so much looking at carbon dioxide in the atmosphere, but working out where it's coming from. And that's called flux. And carbon dioxide flux at Earth's surface is something that we're involved in, where we've built a technology called WOMBAT, which is the Wollongong methodology for Bayesian assimilation of trace gases. And that particular technology is in operation now. And rather than just staring at Earth's surface and measuring the amount of carbon dioxide in the atmosphere, this technology is an inversion, Bayesian inversion technology, very highly sophisticated statistically, that tells us what's coming out of the Earth's surface, not so much where it went to when it's being transported by the wind and by the atmosphere. So, Nabil, I'd like to leave it there. I'd like to thank you very much for your patience, particularly as I was able to get the screen share going. And I'll stop sharing now and be happy to take any questions.
Well, thank you very much. It's really interesting and valuable presentation, Noel. I really enjoyed it, and thank you for sharing all of your thoughts with us. And I'm curious about when you've shown the graph of the last one, I was thinking like, okay, when is the breaking point? Because by Earth could absorb until when? Because I think that if you are adding like a regression model or something, we can predict where is the breaking time that it can't take any longer and might just start to fail. So I think that you have thought about this. And
well, sorry, go ahead.
Yeah.
It's a good question. And it comes down to what you call global geoscience, which is a bit beyond my capability. What I'm able to do is to show what's been happening and to give some indication of what is going to happen in the future. I have, you know, that technology which I shared with you is a way of monitoring how bad it could be. So if we go back and we see that trend, and actually probably the best one to do is look at the yearly trend. And I drew a dotted line at 2 parts per million, and there's no way in the future that we are going to improve on that. If we can start putting that trend below 2 parts per million, we have a chance to avoid, if you like, overloading our oceans. Now, I can't tell you when the oceans might say, you know, I just can't take any more of this. And then we start to see that yearly trend, you know, which is hovering around 2 parts per million, start to work its way up. And if it does that, you know, my technology can say, warning, press the big red button and, sound the warning that we are not even managing to do better than we did in the past, that we're doing worse than we did in the past. And we cannot rely on oceans. We have to really come up with some very innovative, what's sometimes called environmental engineering solutions. Some of those solutions are a bit scary. One such solution is to put particles into the atmosphere. I'm not saying that that's what's going to happen. I'm just saying that, physicists can hypothesize what will happen. It's well known that when there's a large volcanic eruption, and I think Mount Pinatubo in Philippines 10 years ago or something, maybe 20 now, when that erupted, we have very cool summer. And so particles from volcanic eruptions, it's well known that tends to cool. I think there was a mini ice age, maybe 300 or 400 years ago, that well known that was caused by a major eruption of a volcano. So we know that particles in the atmosphere cause cooling and dimming. So the scary thing is, well, are we going to just put some particles in the atmosphere and deal with this climate change? And of course, it could go the other way. We all know about, humans trying to control nature, and usually it's the other way around when, nature says, oh, I'm not so sure about you putting particles in the atmosphere, you put too many in. And when you put too many particles in, perhaps we'll go into a deep freeze. So, we try to turn off a switch and we end up turning on a switch. So these are kind of environmental engineering issues that do come up. There's a third way where you could essentially plant more trees. And we've heard about, it's important to plant trees because they absorb carbon dioxide. Trees need water. And so if you plant more trees, then you start to deplete the water table. So there are unintended consequences. There's one possibility that looks really intriguing, and that is in the oceans, kelp and, all of these, what you might call the forests of the ocean, actually are very quick growing, and they act very quickly to absorb carbon dioxide from the atmosphere. All of these are possibilities to deal with this problem that we don't seem to be able to control, but they have to happen really quickly, I think. We're all kind of stunned, and by we, I mean, the climate community. We're stunned at how quickly climate change is happening. The fact that 10 years ago, what we might be seeing this year and what we saw last year and we're going to see next year, we're all thought that was going to happen in 20 years, not in 10. And so the future is coming very fast. I'm sure there are climate scientists who said, I told you so. I mean, this is happening exactly the way it should. But I think what surprised us all was how quickly the temperature rose as a function of the greenhouse gases. So we're now at like 1.1 or something like that beyond industrial period. So we're in this situation where we're sort of dealing with the future very, very fast, and some solutions will have to be found very quickly.
Yeah, that's the problem, because I think also it's an industrial economical problem, because if we shut down one of the countries like China, all the industrial issues were going to move to India. So we didn't do anything. It's like, I mean, okay, one country could control the CO2 emission at a certain point, but the other countries were going to take advantage. Let's gain all the industrial issues and let's do. So we're going to have the same amount of CO2 emission through different cities or through different countries, but it's always going to be the same. So I'm not a scientist related to CO2. So is it going to be distributed among the planet or going to always be focused on a specific country? This this concentration?
So part of the COP, the Conference of the Parties, the COP, one was held in Sharm el Sheikh, and and then Dubai, and then I think it was in Azerbaijan this year. So those COPs are trying to get at these issues. What are we going to do about it now? How are we going to deal with it? And this year was all about finance and all about getting money to countries who are less well off. But what's happening, of course, is that societies like mine in Australia and the United States and first world countries and beyond, for that matter, is we have an insatiable desire for energy. That energy is expensive, and it's not just energy to turn the lights on. If you've been working with ChatGPT, ChatGPT is driven by very strong computer farms, big servers that are sitting out in the field somewhere that you may not know about. They've got fences around them that are consuming enormous amounts of energy. And so we, as a society, have an insatiable desire for energy, and it just seems that won't go away. We think that our living standards, in fact, it's true, our living standards require a certain amount of energy per person, and different countries have different needs per person, and then you multiply by the number of people, and you're looking at total energy consumption. And so you're quite right. What happens in China is not going to affect what happened. Well, we can't turn that off. We can't turn any country off. But what we can do is look at what the contributions are of carbon dioxide, for example, per country. And one of the agreements in the COP, the original one, the one in Paris, COP21, one of those agreements was to do what's called a global stocktake. And the global stocktake was to find out from each country what their consumption was in 5 years' time. And that global stocktake was done a year ago, or maybe two now. No, a year ago. And there will be another one in 5 years' time. And because the Conference of the Parties, the COPs, made commitments, national determined contributions, they're called NDCs, they made commitments to reduce the amount of greenhouse gases by 24 to 26% by 2024. There were all these commitments made. There needed to be a check to see whether the countries had met their commitments or not. And that's the global stocktake. And I was involved in a large article that was published last year, where we took each country's contribution based on what we saw from the satellite images, and we computed their contribution. We could not do it for small countries. Obviously, a country that is on the order on a Pacific nation, we have no idea. But larger countries the size of Turkey and perhaps Egypt, I'm not sure, I don't recall, but we were computing how these nationally determined contributions were being gauged for basically countries like United States, Australia, China, certainly, and then a number of other countries down to about the size of Turkey. And so these naturally determined contributions are part of the country-by-country monitoring. Now, what I've done is I've looked at what the effect is in the whole of the Northern Hemisphere. And I've looked at that effect and I'm going, this is not working. Whatever COP is saying they're doing, whatever the individual countries are claiming, it's simply not working.
Yeah.
Yeah,
thank you very much. I'd like to open the floor for further questions, and I have Randa and then Amin for further questions. Rhonda, if you'd like to.
Thank you so much, Professor Noel, for your interesting presentation. And also it was very informative. Thank you so much. And we came from an architecture and urban planning background. May I ask, how can the data from OCO2 influence urban planning decisions, especially in designing low-carbon cities or optimizing urban infrastructures to mitigate CO2 emissions? Are there specific examples or approaches where such data has been or could be applied?
Yeah, so it's a really good point, and there is a group in NASA. By the way, I forgot to acknowledge, my collaborations with NASA. I'm actually an affiliate of the Jet Propulsion Laboratory of NASA, and there's another instrument called OCO3, and I vaguely mentioned that there was an instrument on the space station. So OCO2 is an polar orbiting satellite. So it does not concentrate on cities. It concentrates more on which, meridian of longitude it happens to be on at that time. But the space station actually has a different orbit. It doesn't go around the poles. It actually oscillates between about 40 degrees south and 40 degrees north. And it has the opportunity to focus, to target different cities. And so I know this is a US satellite, and they have targeted a number of US cities. In particular, they have targeted the Los Angeles basin. And they're going through Los Angeles is in deep trouble right now, of course, with fires, but let's just put that aside. The satellite, I'm sure, is looking at that and looking at the carbon emissions from the fires in Los Angeles. But let's think about Los Angeles under normal circumstances. So one has the opportunity to do what's called snaps, which is basically, taking a snap of the Los Angeles basin on a targeted basis. And the accuracy of the satellite is really very good. Now, the Los Angeles basin is quite big, but you could probably get 6 or 7 snaps on a particular time of the day of the Los Angeles basin. And what you're seeing then, of course, is the carbon dioxide, which is being emitted by the city. At the same time, there is actually a monitoring station near the Jet Propulsion Laboratory, which is telling us what that particular monitoring is seeing. So there's an opportunity to do some calibration to say that what you see in the basin and what you see at this monitoring station is roughly the same. So it's possible to sort of adjust those snaps and then to move on. Now, what you're able to do is in any year, you might get, at least 12 snaps, but maybe more like 20 or 30 snaps. And you can look at what the effect is of the Los Angeles basin and what their carbon dioxide footprint is like. At the same time, what we have is what called bottom-up estimates. Now, bottom-up estimates where somebody estimates the number of vehicles that are traveling in any one day in the Los Angeles basin. And then somebody estimates the emissions of carbon dioxide or fossil fuel from those vehicles. Somebody estimates the amount of emissions from, processing plants involving oil refinery. And as we know, there's a lot of, excess carbon dioxide from that. And then there might be another plant which is making plastics. And we know that there's some fossil fuel emissions from that. So this is taken seriously, and I'm sure Egypt has its own bottom-up estimates. I'm sure somewhere in your government, somebody is being tasked with working out how much Cairo, for example, emits of carbon dioxide, or perhaps if not Cairo, maybe how much the whole of Egypt emits, because you need to have these nationally determined contributions. And if the satellite can't give you good figures. At least you can get figures from these bottom-up estimates. It would also involve how many trees that you've planted, or the vegetation, and how much that absorbs carbon dioxide from the atmosphere. So I know you're very interested, your group, in urban planning. And so to sort of wrap up the conversation, OCO3 has the capability to look at large urban areas. Now, the question is, can we convince the OCO3 team to target Cairo, for example, if Cairo is your interest? And I have not seen in any of the plans that Cairo has been targeted by OCO3 to what the urban footprint is. Because it's a US satellite, they mostly do US cities, and in particular the Los Angeles basin. In the absence of the top-down is the satellite looking down, but in the absence of top-down, these bottom-up estimates are giving people some idea of the progression of carbon dioxide. And I don't know, Nabil, whether your group is at all kind of moving in that direction. So what is the carbon footprint of each individual? How many individuals do you have in the city? Multiply that up, and then you're going to see a really large footprint, typically, from a city. You'll look at the industries. These are sorts of things, these calculations are being made. They're not impossible to do. They're very difficult to be very accurate, because, you know, you're looking at the average emission of a vehicle, and some vehicles emit more than others. But that's the sort of calculation that's made, and it's called bottom-up estimation.
Thank you so much.
Yeah, that's an interesting, and I think that a lot of research groups are doing this. They have their own weather stations. They try to have some sort of spreading data loggers to try to capture on a micro scale. And I think that this is really interesting. We have another question here, if you do have the time.
Sure.
From Amin. Amin, if you'd like to share your question, or can say it for you if you wish. We can say it for you. Maybe you're not ready. So the question is in the chat box. What happened to the aquatic organisms when oceans absorb a lot of carbon dioxide? Because it needs to fit this industrial with catalytic converters, maybe.
Yeah, well, what happens is carbon dioxide absorbed by the oceans is, you know, if you add water, H2O, and carbon dioxide, you get carbonic acid. And the oceans are more acidic. And some organisms can handle that better than others. Right now, I think that's probably not the big issue. The big issue is not so much chemistry, it's more like the fact that the atmosphere is warmer, and the oceans, in the first, say, 10 meters or so, that the sea surface temperature in the oceans tend to warm. And so the warming of the oceans is really caused by the warming of the atmosphere and the atmosphere-ocean interaction. Now, in Australia, we are very proud of our Great Barrier Reef and the coral that exists in the Great Barrier Reef. But we've had, in the last 5 years, 2 or 3 major bleaching events. And if you could think about a heat wave in the atmosphere, you know, where it happens, Australia is in a heat wave now, and I think in Egypt you're well aware of heat waves, and it's a very hot climate where you are in the summer and beyond probably. But if you think about a heat wave in the ocean, in other words, you know, there are the temperature of the ocean is not a constant by any means, and it moves around, and there tends to be a warming of the ocean in general globally. But what that means is there are instances that occur that are hotter than the average ocean. And it's a well-known statistical fact, actually, that if you take a distribution and you move its mean just slightly, you could double or triple the number of extreme events in the tail of the distribution. So that truncation that occurs if you just move the mean a little bit, and that's what's happening in the atmosphere and in the oceans, actually. Our global temperature is only increasing by, I don't know, it's now 1.1 degrees, it's going to go to 1.2 degrees above industrial activity. But what happens is that average of 1.1, 1.2 means the extremes are actually double, triple, incredible increase in the extremes that happen. And that's a statistical fact. And that's true in the oceans as well. While the average temperature of the ocean might actually not move by much, if you take a global average, you start to look regionally. And, it's not just Australia's barrier reef, it's Indonesia's as well. These countries that are in this region that we occupy as well are going through, ocean warming, not by much on average, but it means that the extremes happen. And the coral, of course, can't handle the extremes. It's well known if somebody tells you, can I cross that river? And I am, I don't know, 1.8 meters tall, and that person says, yeah, no problem. On average, you can cross that river because the height of the river is on average 1.8 meters tall. Oh, but I forgot to tell you that in the middle of the river, it's 3 meters deep. And, you're not going to get across the river. I mean, that's the point, isn't it? That extremes are really what we try to live through and sometimes can't. And so it's the extremes that we should be worried about. And what I've shown you in those maps, there's a certain amount of averaging that I've done through the filtering. I had to do that because I want to get rid of the noise. Once you get rid of the noise, you've got signal. What you need to do then is take that signal and then look for the extremes in the signal. And those maps which I showed you and the filters that I showed you were indicating where the extremes are occurring. And so I don't have any solutions. I don't think anybody has, to be quite frank with you. I talked about environmental engineering and putting particles in the atmosphere, but I'm not really suggesting that that should be done at all. I'm saying that that is a very extreme way of thinking, and we need to be thinking a little bit more outside the box. And so it's a long answer to the question about, what's happening in the oceans. But what will happen, of course, is as the oceans become more acidic, there will be a change in the what I'll call the flora and fauna of the oceans, right? We usually think of flora and fauna as terrestrial, but even down to the notion of the animals of the ocean are basically zooplankton, very tiny in the bottom of the food chain, very tiny things like shrimp, but very, very small shrimp. And they feed on phytoplankton, which is the plants of the ocean. And of course, we have kelp and various seaweed and things as also. But any change to those very, almost microscopic organisms are going to have a huge effect on the health of the oceans. And, well, I'm sure, Egypt has coastline and you have fishermen and people trying to make a living. In where I live in the Pacific, there are many, many Pacific Islanders who only have fishing as a way of making a living. So I'm just going to say we have a beautiful planet. It's a wonderful, rich planet, and we're not treating it very well. And I'm not all that optimistic. We have to really make some sort of change. By we, I'm talking about the planet itself or the nations. And the COPs are a way of getting the nations together, and at least they will make a commitment. What we can do as statisticians is to measure whether that commitment is being upheld or not. But I cannot, suggest that China decrease its electricity output. Everybody needs power. I think we're looking at those alternative solutions that say, yes, we can get power and we can decrease our carbon dioxide, and that would be through green energy for sure.
Thank you very much. I don't know if your time can have one last question.
Sure, no problem.
Dr. Dean, if you'd like to state or raise your question.
Yes, hello, good evening, and hello.
Yes, we
Hello.
can hear you very well. Yeah.
Yes, hello. Thank you, Professor, for this type of really eye-opening presentation to have the whole picture. And from the background of construction projects, specifically architecture and engineering, I have a question. If we are having a new practice or an experiment to mitigate the negative impact of this practice in the field of architecture and engineering. So there is a type of a tool to a real-time monitor this type of practice in order to reach decarbonization or reduce the carbon footprint.
Yeah, so I'm not an expert in that. I'm more of the remote sensing sort of a person, but I do know, and I'll just share with you, there are about 30 monitoring sites around the world, not many, and it's part of what's called TCON, which is the Total Carbon Column Observing Network. And there are those 30 stations or so are not distributed particularly evenly around the world. And so I'm not sure whether there's, I know there's none in Egypt. I know that for sure. But what I'm getting at is that that particular monitoring instrument is extremely sensitive. And the TCON network of scientists, and we have one in Wollongong, by the way, at my university, it's because it takes the contribution of a country and or a university to set up that monitoring network. Now, what it lacks in spatial extent, it makes up in time, in temporal extent. So in any one day, you could get, I don't know, 300 observations of what the carbon dioxide is in the atmosphere above Wollongong, for example, or above Los Angeles, or above Bremen. I can, and there's one on Reunion Island, which is a French territory, which is trying to capture carbon dioxide in the middle of the ocean type of thing. So there are these instruments, they're quite expensive, but because they're monitored and calibrated very carefully, what we do is we use those instruments for the satellite, and the satellite looks at Reunion Island and it targets it for some of the time that that particular instrument is measuring. And then it says, I'm going to do an XY plot. I'm going to do a regression. I'm going to work out this really accurate measurement that I have on the ground. I'm going to see what the satellite sees. And then I'm going to adjust what the satellite sees because I know the accurate measurement on the ground exists. So, I mean, in your work, you're obviously really interested in how a city or how a suburb, what its carbon dioxide footprint is. And to my knowledge, apart from this bottom-up estimation that I talked about, where you work out how many cars and how many people and try to come up with a footprint per person, a footprint per car, and if there's any industry. From my knowledge, apart from the bottom-up estimate, I cannot think of a way to have a really good measure of carbon dioxide above that region. Of course, you can buy cheap carbon dioxide monitors and you can put them in rooms, And there it's being used for a different purpose. It's being used to make sure that you have good air quality. But the effect of the greenhouse gas carbon dioxide, which is what we're worried about, the effect of that is felt, you know, at 3 or 4 kilometers high. You know, it's not at the room effect. It's more like what is coming out of Earth's surface and working its way up into the atmosphere and forming a blanket across Earth's surface and keeping the heat in. That's really what the effect of carbon dioxide is when it comes to climate change. And I don't, other than this bottom-up estimation, I don't know of any other way to measure it. And so, I mean, why are we measuring this? We're measuring it because we can actually mitigate. We're trying to do something about it. If we have good measurements, we could say, oh, well, I'll change this. And then you look at the effect and say, well, that worked. That was good. And so, you know, I'm sort of more interested in these global issues. You're interested in local issues. Now, Bill's asked the question about country, you know, regional issues, where how countries might actually contribute or not contribute. I think that's where the action is, to be quite frank with you. We can all do things locally. There's no doubt that, you know, if we provide a lot of shade from trees, the heat island, you know about heat islands, I'm sure, the heat island of a city is a lot less, and that does us well with temperature. But in terms of carbon dioxide, it has to be at this country level. And while I'm a bit cynical about the COPs, you know, the Conference of the Parties and how it's not worked, I can't think of anything else, because every year there's a commitment that, I don't know, 160 countries will get together and they'll say, well, how do we do? Or what can we do next? At least they're talking. Antonio Guterres, the United Nations Secretary General, had a New Year's greeting for the state of the climate. And I don't know if you heard that, but he was just talking about a roadway to hell, I think is what he said, or something like that. Something quite extreme. And what he's trying to do is kind of scare all the countries into saying, well, let's get serious. We can talk, but now we have to have action.
Yes, truly. Thank you very much. And really, on behalf of our community and lab, we really thank you very much for this valuable discussion, presentation, and you have opened a lot of issues that we should consider, not on the scale of our lab, but on scale of our country, and we need to act. Yes. So thank you very much. Thank you. And do you would like to add any last words for this webinar?
No, it's a great pleasure. And to find out about your lab as well. When you contacted me, I started to look you up and I saw what you were doing. And I said, Nabil, I'm not sure if my more global point of view is of interest to your group, but we all live on this planet and we all have to share it. And I admire what your group is doing, so do more of it. You've got to build better cities, and architecture is all about how people move in spaces and how they feel good in their spaces. And I know you're trying to do that, and so congratulations on that. I'll just try to make sure these countries stop emitting carbon dioxide if I can.
Thank you very much, and see you all, and have a nice day in the morning at Noel, and have a nice night in our side in Egypt. Thank you very much.
Well, thank you, and thank you for the late evening talk on your part. Goodbye now. Take care.
Yeah, you too. Bye.